It's a pleasure to welcome you to the inaugural session of the lecture series on advancements in geotechnical engineering, from research to practice. AGERP lecture series is an attempt toward disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on mining geotechnology, which will be delivered by Professor David Williams and Mr. Mark Reinhardt. Professor David Williams is Professor and Director of the Geotechnical Engineering Centre within the School of Civil Engineering, at the University of Queensland in Brisbane, Australia. David obtained a BE with first-class honours in Civil Engineering from Monash University and a PhD in Soil Mechanics from Cambridge University. He worked for the Victorian State Road Authority and for Golder Associates before joining the University of Queensland in mid-1983. He has an international reputation in the application of geomechanics principles to mine waste management and mined land rehabilitation, and associated issues. He has made important contributions to the development and implementation of pumped co-disposal of coal mine washery wastes, store and release covers over potentially contaminating waste rock dumps in semi-arid climates, capping soft tailings, the hydrology of waste rock and tailings storage facilities, the settlement of high coal mine spoil piles, understanding problematic clay-rich coal mine tailings, and risk assessment and cost-effectiveness analysis applied to mining.
Okay, thank you for that introduction. I'm going to talk a bit about Brumadinho. So really it's about the lessons from Brumadinho, but I'll add a little bit of commentary at the end as well. You've seen a little bit of history, so I'll skip over that slide. Many of you may have seen, if you've got an interest in tailings, you may have seen this video. It was released to the press. That dam was about 80 metres high. The wave that came out of it was at least 30 metres high. You can see that it came out through here, almost out the toe of this water dam on the left-hand side. It took out a corner of this processing plant. It went over the stockpile area. It came out into a valley that then did a right angle bend to, in that picture going to the right there, and it swapped to the other side of the valley where it hit a bit further downstream the canteen where many hundreds of workers were having their lunch, and unfortunately that's where the majority of them perished. It's 270 or so people. The other thing you might notice is that the catchment above the dam is actually quite large. So about 70% of the catchment of the total dam area was above the dam. It's also, I think, telling to look at the early impact of this failure on share prices. So I'm looking just at the last month, or the month following the failure. And I've got Vale, and then three other global iron ore producers, BHP, Rio Tinto, and Fortescue. Now, in order, Vale is dominated by iron ore, but it has some other interests. Rio Tinto likewise. BHP has a lot of other interests apart from iron ore. Fortescue is a purely iron ore play. And you can see that within about a day, the Vale share price was down about 26%. And it oscillated a little bit after that. These little peaks and troughs, they're not based on sound analysis. They're just gut feel on the part of the market. And the market obviously thought it got low enough, and then there was a bit of a buying splurge before it went back down again. That's just the first month after the failure. What's good about this is that nothing much else was happening at the time. So these changes in the share values of these various companies, all connected to iron ore, are a true reflection of the impact of the failure. Notice that while Vale went down in about a day, the others took a few days to start picking up and just continued to go up. And essentially the market capitalisation of all these iron ore producers remained about the same. So Vale's loss was the gain by the others. Looking at the early impact of the failure on the 62% spot price for iron in US dollars, that's the month after the failure. And each of these rises and flats are pretty easily explained. So this initial rise over a day or so was the loss of that particular iron ore mine, and it's steady for about a day. Then it took off again, and that marked Vale announcing that they had a number of other mines that had tailings dams that they were a little worried about. Then the government stepped in again and said, no, you've actually got a few more, and it went back up again and flattened off. And this rise was associated with Vale calling force majeure. In other words, they were worried that they wouldn't be able to meet their their contract sales, and the market quickly scrambled to buy more iron ore. It took a few days, and then it dropped back again. So all of these points, isn't hindsight, glorious? With the benefit of hindsight, you can see exactly what happened, but no one could have really predicted this. So it was up. The iron ore price overall was up by about the same amount as Vale went down. So what of ongoing tailings dam failures? The average failure rate is about 2 per year. That's the ones we know of in the last 100 years. It hasn't changed all that much. It's about 2 orders of magnitude higher than that for water retention dams. Begs the question, is this acceptable? By most people's measure, no. But the focus is on failures that occur in developed countries, and examples are Mount Polley in Canada in 2014, Cadia in Australia in 2018, which didn't actually do a lot of damage. It didn't go outside the footprint of the tailings, but it still had quite an impact. Or those that involve global mining companies. So this is Samarco, which is a BHP Vale joint ownership in Brazil in 2015, Brumadinho Vale ownership in Brazil in 2019. And the other important thing to note is that tailings dams can fail in seconds and they can fail catastrophically. And we saw this, if you were able to see the movie, but I'm sure you'll be able to look it up on the web. You'll see there that it showed it very dramatically, just how quickly the failure developed and took off. It was all over in a matter of seconds. And these recent high-profile tailings dam failures are threatening the mining industry's financial and social licenses to operate. And they're threatening the industry's control of its own destiny. There's a danger for them that they'll be told what to do. So what are some of the key causes of tailings dam failures and what are the industry threats? Well, firstly, most tailings dams that fail have marginal stability. There are many tailings dams, obviously, that don't fail. Most tailings dam failures involve water. So that makes drainage, clay cores and water management key. It's a bit like in politics, they say it's the economy, stupid. You get the economy right and you'll be re-elected. And the vice versa is also true. Now, in the case of tailings dams, it's the water, stupid. Many tailings are potentially liquefiable. They're put out as a slurry and often remain in a semi-fluid state. Another cause may be a weak foundation. And the industry threats are coming from investors. So following the Brumadinho failure, the Church of England, a substantial investor, started asking some very awkward questions about the stability of tailings dams among the members of the ICMM, the National Commission on Mining and Metallurgy. Also insurers. There are insurers who are questioning whether they should insure tailings dams, and a lot of mine operators are having a lot of trouble getting insurance. Some of the bigger companies have gone for self-insurance, which essentially means that the shareholder wears the risk. And the regulators. So for example, outlawing upstream construction, which happened in Chile and Peru following earthquake-induced failures in 1965, and it followed in Brazil's wet climate in 2020. So now I'm going to switch to learnings from the expert panel report, and I've indicated there the website that you can get the full report from. So that's the report, the appendices, and a commentary. B1 technicalinvestigation.com. So firstly, the terms of reference of the expert panel. The investigation was commissioned by Vale, the owner of the mine. The expert panel was instructed to use its expertise and professional judgment to review and assess requested relevant information and technical information to determine the technical causes of the failure of Dam 1. The technical causes of the failure of Dam 1. The expert panel did not assess matters relating to potential corporate or personal responsibility for the failure. The panel relied on assistance from consultants, but the conclusions presented are those of the panel. So just to locate where we're talking about, location of Dam 1, this is a ridge that separates, This is the ridge that separates Belo Horizonte, the third largest city in Brazil, and there largely because of the iron ore resources of Minas Gerais, the state. The ridge there, and many of the mines are actually located in the iron-rich ridge. Down here is the town of Brumadinho. There's a river that separates the town from the hill that goes up to this ridge. There's the mine, there's the overburden dump, there's the water dam that was almost taken out by the failure, and that's Dam 1, the one that failed. So you can see that when Dam 1 failed, it progressed in this direction and then went down the valley, crossed the stockpile area, wiped out most of the canteen, and ended up stopping just as it reached the river downstream. there wasn't enough volume left to go any further towards the town of Brumadinho, which was obviously indeed fortunate. Now these references down here in italics are figure 2 in the report, the expert report. So what made Brumadinho tailings different? How are they different from normal soils? The tailings were high in iron content. And in fact, some of the tailings were as high as 90% iron. So the tailings were actually richer in iron than the ore, which is probably more like 70% or 60%. And this iron oxidized to form bonding or cementation. The result was a high peak shear strength, an undrained shear strength ratio, that is shear strength to effective stress, of 0.34. The design value is 0.26, but it occurred at very low strain, less than 1%. And the liquefied strength ratio was negligible, very much less than the 0.05 that many people presume for the liquefied or post-liquefied strength. The peak drain friction angle was high, much higher than the critical state value of 34 degrees, so it wasn't going to fail in a drained fashion, it was going to fail in an undrained fashion. So here's the bonding, if you like, and you can see that these are particles of tailings. Now this is a scanning electron micrograph, there's 25 micron there. And each of these particles is surrounded or cemented on finer particles, and then there's cementation between these larger particles. So there's bonding or cementation, if you like, at every scale in this picture. And they weren't originally like that. The particles were originally fairly clean, but these are the oxidation products. And then down here is a schematic of the undrained shear strength ratio to vertical effective stress as a function of vertical strain. So it's just diagrammatic, but showing that it's very brittle behavior followed by negligible, at relatively low vertical strain, negligible post-peak strength. If the material were more normally consolidated, more like a normal soil, that dotted line would be something more like the behavior. And it would then come down and eventually come to a lower value, but perhaps a lower value of about 0.05 strength ratio. Now, here's an example of cone penetration data for Dam 1 tailings. The cone has become probably the go-to tool when you look at trying to test tailings because they're very difficult to sample, difficult to retain samples when you use boreholes and so on. So the cone has become the sort of default tool. And you can see how the data plots here. Now that line, the curved line there, represents a value of 70 on this plot. Notice also this is a log plot. In fact, more than that, it's a normalized cone resistance log plot. This is a normalized friction ratio log plot. And we all know why we use log. We use log to try and linearize things, but even on that linearized plot, all these lines are curves. And this is an estimate of the boundary for non-liquefiable versus liquefiable. So dense on the upper side, loose on the lower side. So the tailings below water level are potentially contractive or loose at large strain. Well, actually not at such large strain because they're cemented as well. So you can see the bulk of the data fit below this line. Now you might say that this value of 70 should actually be a bit of a range. You know, it's probably not entirely reliable to have a single curve there. Perhaps you should have a range where you've got a transition from loose to dense. So that's typical cone data. You can see that whichever way you wash it, the material is potentially liquefiable. These are the critical state lines for typical Dam 1 tailings. So we did testing on the average, the finer fraction and the coarser fraction. And you can see that these critical state lines, first of all, they're curves, they're not straight lines. And secondly, they're pretty much parallel, but they're displaced vertically on the void ratio plot, depending on which gradation you're looking at. Now, we didn't necessarily have average, fine, and coarse, but we had coarser material towards the dam. We had the finest material further from the dam, and the average somewhere in between. But it turned out to be important to differentiate between these three gradations because there's quite a range of void ratios. So monitoring and the failure. So because of the Fundau failure about 3 years earlier, also in Minas Gerais, there was a lot more monitoring, in fact, a lot more investigation of the Brumadinho site than there would have otherwise been. So they had piezometers, but piezometers are often slow responding. So if you calculate how long it takes for a piezometer, a standpipe piezometer to respond, it's minutes in sand-sized tailings, it's days in fine tailings, and it could be about a month in the slimes end of the beach, at the far end of the beach. So they were replaced. They were originally just open standpipes that were dipped, but they were replaced with vibrating wire piezometers, but still in the open hole. So their response time was still relatively long, depending on what material you're in. They were automated prior to failure, but there's a relatively short record of automation, and the frequency of readings was not all that close. But they did show a slow lowering in the phreatic surface within the tailings. Now, the tailings they'd ceased to deposit tailings about 3 years earlier. But the lowering of the phreatic surface was only about a metre in the 3 years or so post-deposition. The cone data were used via the water pressure dissipation to give an idea that it was actually non-hydrostatic. So because there was seepage coming out of the face, that drew the pore pressure distribution down with depth. There were inclinometers, but they weren't fixed, meaning that the whole of the inclinometer could have moved, and in fact the inclinometers showed variable responses in both directions, so they were not relied upon. There were servo monuments and there was a total station, but there was insufficient precision from that system to give you the sort of movements they were getting prior to the failure. They installed a ground-based radar, which had been taken out of the pit, but unfortunately that exhibited a lot of noise. Now the noise comes from the fact that ground-based radar is based on microwave frequencies, and everyone who knows about microwaves realises that they respond to moisture. So when you've got a vegetated slope and variable moisture, you get a lot of noise. There was more noise than there was actual movement. So there's no discernible deformation. They had seismographs, but they recorded no earthquakes or blasts at the time of the failure. They had, importantly, the video cameras, both on the front, the one you would see if you looked it up, but there was also one on the back, which showed the regressive nature of the failure. So they showed the deformations as failure took place, not before. And there were satellite images which hadn't been addressed before the failure, but they were afterwards, and they showed ongoing creep with some wet season acceleration. And the failure was sudden, catastrophic, with no apparent precursor. So none of these monitoring devices gave a definitive precursor to the failure that was about to occur. Probably the closest that came to them were the satellite images, but they weren't analysed until after the event. Now looking at the cross-section, so this top right-hand corner one was what was used by the designers, a typical cross-section. And you can see the different colouring, that the darker raises were tailings, constructed out of tailings. The lighter ones were supposedly constructed out of laterite, or locally one with biomaterials. This one down here was encased. There was a deliberate attempt to encase the starter dam to make it low permeability. And in fact, that low permeability zone, or that encasement or sealing layer, went up to the top of, almost the top of the second lift. There was a setback here, and the slope below the setback was steeper than the slope afterwards, but by having a setback, it means that these raises are placed further back on the beach, a poorer foundation, and it makes that zone there particularly susceptible to failure because you've got weak tailings in front. So you might think that you've lowered the overall slope of the dam, therefore it should be more stable, but locally it's not. So the expert panel decided to change somewhat the sections that were analysed. Some of the sections they had were actually not straight lines, but they had a kink in them. So we looked at these three typical cross sections, and section 3 was the critical one of those, and it looked like this. And these layers were inferred from all the data we had available, mainly cone data, a little bit of aerial photography as well. So you can see the raises. You can see the yellow is the coarse tailings, the orange is the fine tailings, and the red is the slimes further back. Now they appear to sort of truncate very rapidly, but that just reflects that we had data either side of that point. We arbitrarily decided to truncate those layers, but in fact they would feather out in reality. And that's how the section looked after the failure. This is looking at the left abutment, and you can see clearly that this uppermost 10th raising was constructed out of tailings. This was boromaterial, and then most of the rest were tailings apart from this one. not quite the same. The as-built was not quite the same as the as-designed. And if you look really closely, you can see there are some drainage layers along the base of each of those. The other thing you'll notice is that the toe of each raise sits on the upstream crest edge of the one before. So each of these raises sits entirely on tailings. There's no overlap with the previous raise. So there were some potential technical causes of the failure that were discounted. There was drilling for deep horizontal drain. So the idea of this was to try and lower the phreatic surface further. They put in 3 horizontal drains at the upper level. They put in 9 at the setback, and they put in 3 in the end towards the toe. And one of those, deep horizontal drain number 15, went through the starter dam. It was put in 7 months before the failure. It resulted in the emergence of turbid seepage 15 metres from the hole and about 7 metres vertically up from the hole, so that's 70 kPa, accompanied by a rise in nearby piezometers. There was a seismograph response to this failure, of localised failure, and there were measurable deformations and relaxation of the dam face. But it happened 7 months before the failure, and we can't ascribe the failure to this. There were no earthquakes or blasting. Between October 2018 and the time of the failure, 9 instrumentation boreholes were drilled in the dam, but no signs of distress were detected. These were instrumentation boreholes for vibrating wire piezometers and also further inclinometers, none of which were completed before the failure occurred. In general, water levels within the dam were either slowly falling or remaining essentially constant prior to the failure. So the technical causes of the failure. First of all, the dam 1 was marginally stable. In simple terms, it was oversteep and too wet. About half the volume of this dam was water. About half the volume, not the mass, but half the volume was water. There was a sudden strength loss and resulting failure of this marginally stable dam due to a critical combination of ongoing internal strains due to creep and a strength reduction due to loss of suction in the unsaturated zone above the water table caused by intense rainfall towards the end of 2018. This followed a number of years of increasing rainfall and intensity after tailings deposition ceased in July 2016. So that's about 3.5 years before the failure. The calculated pre-failure strains from this combination of triggers match well the small deformations of Dam 1 in the year prior to failure that were measured and calculated. It's also important to note that conventional limit equilibrium analysis assumes all points on the slip surface are at the same state. Now, if all points on the slip surface in this case had been at the peak of bonded strength, the factor of safety would have been of the order of 1.5, but it was actually closer to 1. And the reason was that parts of the dam had already passed their peak strength. So these are some images taken from the front video over time. You can see that time span is only 3.6 seconds, 3.6 seconds. And by looking at the images, our analyst was able to note the difference or the change in deformation, both upward and downward, the vertical deformation just from this video, looking at frame by frame. So the onset of failure was actually at the crest. Many people thought it was down here somewhere because visually that's perhaps what you picked up first. If you looked at the video, you'd probably pick up that creasing that occurred down here first. But in fact, it was settling at the crest first. Then this started to develop as the crest settled further. Then you got more deformation at the crest, more at the crease, more again, until eventually these two started to join. And when it took off at about 3.6 seconds, the whole face, or 2/3 of the face, was on the verge of failure. These are some data from satellite INSAR. There was some post-failure analysis. And each of these vectors, just to give you an idea of scale, that's 5 millimeters per quarter. These were the 4 quarters prior to the failure. And just so that you can see them, they've been displaced downwards. But in fact, they're all relating to a point on the surface. So for those 4, it's relating to that point. You see my cursor? And for the crest, it's relating to those ones, it's relating to this point. You can see that essentially the deformation was near vertical with a bit of a kicking out towards the toe. And as you went back in towards the slimes, we found the deformation was greater, but it was entirely vertical, and that was a result of ongoing consolidation settlement of the slimes, but the face was actually deforming. Now this is looking at the unsaturated zone. Now that's the foundation level. This is the phreatic surface. It's a calculated phreatic surface based on all the piezo data and piezo cone data that was available. And the reason why you see some of these returns is because of varying layering, so fine and coarse layering. In reality, it would be a much smoother transition, that phreatic surface. And in fact, this effect confused some of the other designers involved, because it suggested that there was water emerging at various points down the face. For example, that point, that point, that point, and then down here, which was probably the case. And they inferred from that it might be perch water tables, but in fact they're not. They're just a function of the layering and the fact that in places the water table came close to the surface. So that's the whole storage. That's just a detail of that box there. And you can see there's quite a substantial portion of the tailings which is unsaturated. This is looking at cumulative rainfall from, that's essentially the summer, August to January, cut short in January because January is when the failure occurred. And we're looking at the last 6 years prior to the failure. And you can see that the dark line, the dark black, the heavy black line is the 2018-2019 rainfall total up to the point of failure, which was the 25th of January in 2019. And you can see that generally it's the upper bound to the other data. There's up to a factor of at least 40% or so more than some of these earlier rainfall events. So there's a gradual increase in rainfall towards the fateful one before failure occurred. And I've just highlighted for you some of the intensities. So more than 200 millimetres in 26 days, 266 millimetres in 11 days, 484 millimetres in 42 days, taking those two together, 128 millimetres in 9, and 225 millimetres in 16 days to the 4th of January 2019. So it wasn't raining at the time of the failure, but they had quite a go at rainfall prior to that. So this might take a little bit of getting your head around, but this is a plot of elevation against pore pressure. This is the zero pore pressure line. If you look at all the lines, that's a gradually dropping water table. The maximum drop was 3.5, the average is about 1 metre. So I put in a zone as to indicate where the water table was, or phreatic surface. And you can see that up to about that point, the curves are pretty much coincident. There's not much going on. And you can see that the average line through the data below the water table are roughly half the hydrostatic. So this is a result of seepage coming out of the face, drawing that water level down, or that pore pressure distribution down. And where you've got jumps is a function of the layering, fine and coarse. Now what's important is to look up here. So you've got from 1st of January 2016 through the 25th of January 2019, you've got this gradual wetting up. You're losing suction. And as you lose suction, it's equivalent to a loss of strength of up to 15 kPa. So there's this general loss of strength. So what's happening is the rainfall is infiltrating, causing the unsaturated zone to wet up. The unsaturated zone doesn't have sufficient permeability to let the water go any further, so it's not getting much below about that level. So all this action is happening in the top 25 metres or so. And there's a disconnect between this unsaturated zone and the saturated zone below. So low permeability unsaturated zone and the saturated zone below, a disconnect. Now here's an indication of one of the deformation modelling of the failure. This is a little hard to read. That's the setback there, that's the lower part of the slope, that's the upper part of the slope, that's the tailings in behind. And you can see that all the activity is concentrated around this setback. So it's quite possible that setback was not a good idea. So going back to that diagrammatic plot I gave you before of the undrained strength ratio versus vertical strain, remembering that's the sort of relationship we have with this bonded material. Let's try and work out a schematic path to failure. which is essentially a strength reduction due to loss of suction and then ongoing creep, which took it from this point to that point. Now I could have made this these two vectors at any starting point on this curve. I chose to do it there, but you can move them around. You can put them there and there. You know, the different parts of the tailings would exhibit different strength reduction, different ongoing creep effects. But the point is, you go from a strength up here to strength down here, and that's enough to turn this marginally stable dam into something that was unstable. So this critical combination of strength reduction and ongoing creep led to the failure of this marginally stable dam. So now I want to turn away from expert panel work and just to some general learnings and observations. And then we'll open it up for questions after that. So some general implications of tailings dam failures for practitioners. There's a loss of confidence and trust in tailings engineers. Loss of confidence and trust. They're two different things. We're not confident that you can do what you're supposed to do, and we don't trust you to do it. And that's going to take a long time, if ever, to restore. Tailings engineers, it's important to say, are in the front line when it comes to failures. And unfortunately, there have been too many of them. It's not the bean counters. It's not the accountants in companies that dictate how much money is spent on different aspects of the mining business. They're not going to be held to account. It's the tailings engineers, the technical specialists who are, and some of the responsible line management people as well. So the ICMM, in collaboration with the United Nations, environmental people, and also the Responsible Investor Group, PRI, has drafted a global tailings standard as part of their global tailings review following this failure. And that's the link to it, globaltailingsreview.org. And the intention is not to replace national guidelines or regional guidelines where they exist, but to complement them. It'll be very interesting to see over time how this plays out, whether the global tailings standard will become legally more accepted or whether the national guidelines will continue in their current form. The other thing I want to highlight is the importance of climate, topography, and the seismic setting of your site. So in the case of miniature ice, they've got two of those working against them. The climate, it's wet, hence they didn't get drained down of their tailings as you might have expected in a dry climate when they stopped depositing tailings. In fact, pretty much they stayed the way they were. And the topography. So you've got fairly high relief in this part of miniature ice. That gives you free storage, if you like. They didn't have a seismic setting, so they weren't triggered to do anything about it because seismic was not a design issue. But the climate and the topography make it critical. So let's look at some responses and changes arising from these well-publicised recent tailings dam failures. Firstly, Mount Polly, which was a foundation failure. Some of the responses. The reinstatement of the tailings dam. So they decided that they'd investigated the failure so well that they knew more about that site than anywhere else. So they decided it was sensible to work with that site and raise the dam at that location, putting in a buttress for stability. There's been what I'd call persecution of tailings engineers by some of the authorities that govern engineers and their work. And it's become quite personalised, not the way it should have gone perhaps. There's been ongoing legal actions against the company, engineers and the government, all of them being blamed in different ways. Some of the changes that have occurred as a result of Mount Polly. There were audits of all the tailings dams in British Columbia. They'd identified about 6 with insufficient information to confirm their stability. That extended to the rest of dams across Canada, and there have been company audits worldwide. Fundau, a liquefaction failure. Prosecution of tailings engineers and executives, which was dismissed. They were initially charged with murder. Remediation of the site and downstream impacts. There's been a lot of work, a lot of money spent. Ongoing legal actions against companies and governments. They'll go on for a long time. The quickest response really is the financial markets, which happens almost in days. Increased investigation, some of the changes, increased investigations and instrumentation across Brazil, company audits worldwide yet again. But what changes to practices? Not much. Then Cadia, another foundation failure. What have been some of the responses? A change to in-pit tailings storage. Reinstatement of the tailings dam. Some changes: increased investigation and instrumentation. In fact, all of the sites have improved their investigation and instrumentation. Fundau in particular is probably the best instrumented site in the world now. Brumadinho, and arising out of that, some of the responses: banning upstream raising in Brazil, remediation being required of dams identified as being at risk, and that work is to be done within a 2-year timeframe, which makes it very tight. Pending prosecution of tailings engineers and executives, and expected further legal action. Then some of the changes: questioning upstream raising, not just in Brazil, but worldwide. And that's probably a little unjustified because you can make it work in the right climate, with the right sort of operating conditions. The global tailings standard hasn't yet been ratified, but that's coming. Again, company audits worldwide. But what changes will we see to practices? We're still sort of waiting. There's been a lot of work on governance, not so much on the actual practice of tailings. Now, I want to highlight this because a couple of plots actually. Because we work in terms of factor of safety, but perhaps we should be working more towards annual probability of failure, or some probability of failure. So this is a plot of those two, and if you had to come up with a unique point, a factor of safety of 1 is essentially a probability of failure of 50%. But on top of this, superimposed are these coloured lines for poor through the best construction, design and construction. Let's see what that means. When the factor of safety is 1.5 and we have poor design and construction, factor of safety might be 1.5, but the annual probability of failure is about 1 in 10, clearly unacceptable. On the other hand, if we had best design and construction, the sort of thing we typically do for water dams, the factor of safety again were 1.5, we end up with an annual probability of failure of about 10 to the minus 6. Of course, it's the log scale. 10 to the minus 6 is the value we normally assume is acceptable for air flight. 10 to the minus 5 or thereabouts is what we normally accept for travelling in a car, particularly if you're a passenger, so it's involuntary. If you're a male driver, then we'll accept probably a lower or a higher probability of failure of 10 to the minus 4 because we think we're invincible. For dams, for water dams, it's about 10 to the minus 4. Now, this is an earlier thing. I've got labelled 2008, but this actually came from Bob Whitman in 1984, talking about the acceptability of risk. So here we've got annual probability of failure again on the vertical scale or log scale. We've got dollars lost and we've got lives lost. Well, dollars won't mean much because this was originally drawn up in 1984. It was probably done around a nice dinner and a bottle of red on a serviette, I would imagine. They started with this plot and they started doodling. So this is water dams, this is foundations, this is mine pit slopes, mobile drill rigs, various other developments. And then they put these two lines in which were to indicate the range that might be acceptable. So if you're below there, unacceptable. If you're below there, acceptable. If you're above there, not acceptable. So it's just a bit of doodling. Now, where would tailings sit? Well, tailings, I'd have it would be something like this. So just on the basis of what we know, lives lost could be nothing through to about 270, which is about there. Best practice, probably 10 to the minus 4. Worst practice, about almost certain it's going to fail. So that's the range. And it's certainly possible to shrink this down to somewhere down here. In particular, to shrink it on the annual probability of failure plot. So think about acceptability. It's not just about risk assessment, it's also about the acceptability of risk. So some of the emerging tailings dam surveillance methods, and at the moment, none of these would necessarily give you a precursor to failure. But among the methods, we've got drone surveillance that's coming more into its own. It's used to aid visual inspection and LiDAR, which is essentially laser from the air. We've got nested grouted vibrating wire piezometers to record and analyse the phreatic surface and the hydraulic gradient, but in real time. Because they're nested, you can get the actual hydraulic gradient. Settlement monuments and fixed inclinometers, they need to be fixed in the foundation so that you're getting a real measure, not just a relative measure. And that would be for correlation with radar and satellite, but they must be high resolution. You've got LiDAR above water and bathymetry and below water for estimating the tailings dry density and evaporation. you've got ground-based radar, but you've got a potential noise issue. Satellite radar, still radar, but it's of a longer wavelength and not so sensitive to moisture. And it's also taken at distinct time intervals with gaps in between, so you don't get quite the same noise. And it can be more accurate. And it's quite amazing that satellite radar can be more accurate than ground-based, given how far away it is. It also picks up other things like wet spots and vegetation. B-notch weirs to monitor flows, environmental monitoring, and then a couple of new things thrown in there: fibre optics and smart geofabrics. Now, they could be installed in the tailings beach or under upstream raises to give you a better idea of what the interior of the tailings is doing, because it's too late if you're only focusing on the face. If things have already moved within the interior of the tailings storage, it's too late by the time you get to the face. And the other possibility may be microseismic monitoring, but it would have to be sensitive, it'd have to be close to the dam, but you'd have to be able to filter out all the other effects that it might pick up, even a truck going past. So how would we monitor to ensure adequate stability and warning of failure? Above all, design, operate and close the tailings dam, ensuring an adequate factor of safety or stability margin against geotechnical failure. Avoid, where possible, having people at risk downstream. Try and give them 24 hours notice, but at the moment we can't do that. Install redundant monitoring systems recorded and analysed in real time and linked to triggers and responses. So daily inspections for wet spots, cracking and deformation aided by drones. Phreatic surface and hydraulic gradient, vibrating wire piezometers confirmed by regular and CPTU testing. And deformation, a combination of automated total station prisms like inclinometers, radar, INSAR, and some of these other things are starting to develop, but we're not there yet. So just to round it off, a couple of innovations in tailings management. On-off tailing cells, the idea of putting tailings into a cell, drying them and then harvesting them and using nature basically to dry them off before that you combine them with coarse waste. Thickening to the extent possible, paste disposal, dry stacking, co-disposal, putting the tailings and of course waste together, been done in coal washery waste in the Australian Eastern coalfields from the 1990s. Not always wonderfully successful because they pump at low percent solids and high velocity, so you still get separation at the fines. You end up with a tailings beach beyond your coarse beach. Integrated waste landforms, can we somehow not mix but put the two in the same storage? Paste rock and geo-waste, which are both patented terms, haven't really so far gone much beyond trial stage. They're seen as too expensive. Tailings reprocessing and reuse. Well, reprocessing in particular might be a cheaper solution than having a tailings dam that must be stable in perpetuity. But all of these things have limited take-up due to their perceived high costs. So what are some of the barriers to these innovations? Net present value accounting and the use of a high discount factor between 6 and 10%. So that favours tailings management that delays expenditure. So it delays expenditure in the short term, but is in turn likely to exacerbate impacts and blow out rehabilitation costs in the longer term. The perceived high costs of putting in some of these management options. The perceived and real technical difficulties, for example, tailings that has a high clay mineral content, or handling coarse grained waste together with your tailings. Resistance to doing what we've always done, and uncertainty about new approaches. And that's it. So, Partha, if you'd like to open it up for questions.
Yeah, so we actually have, I must say thank you, David, first, and then we actually have quite some questions. Okay, so this first question comes from Professor Satish Pisni from Fiji National University. And he asked that you explained the CU was 0.34 and the drain friction angle was 34 degrees, which means that the tailing material could be categorized under medium dense to dense. However, you also have mentioned the material is highly liquefiable in nature. How can we characterize the tailings material in this case?
Yeah, well, the problem here is that while it might have a high undrained shear strength, it's not so much due to its density. that's an artifact of the fact that it's bonded or cemented. But when you break, you know, bonding or cementing is very brittle. So if you break it, if you have enough deformation to break it, and you don't need a lot because it's very brittle, it doesn't need a lot of strain, less than 1%, then you lose all that. And once you lose the bonding or cementation, the material reverts to you know, its roots, if you like, and it's quite liquefiable. It's quite loose, quite liquefiable. So interestingly, the cone data showed this up too, but then it's quite possible that pushing the cone into the tailings was enough to break that bonding. So what you're getting is you know, a true reflection of what the material would be like without the bonding. So we're not talking about strong cementation here. We're talking about just a small amount. So some of the particle-particle contacts are bonded. It doesn't take a lot to break them. And once you break them, the material is then dominated by its loose state, loose or contractive state, so they are liquefiable.
Okay, let's take the second one. So this second question comes from Charles Yang from WSP Newcastle, and he has got two questions. The first question is that, has the suction taken into account while you designed the tailings dam? And what range would the creep coefficient be for the tailings?
Yeah, well, in terms of suction, I don't know that anyone who systematically takes into account suction. So we typically discount it. We don't look at it. It's a safer way to go if you ignore it. But it might also give you a false sense of security that while the suction is there, the tailings appear to be stronger than they perhaps would be if they saturated. And what appeared to happen was in the 6 years or so towards the time of failure, they didn't have necessarily the highest rainfall on record, but they had increasing rainfall every year. So gradually those unsaturated tailings were wetting up, not totally saturating, but wetting up to the point that they lost apparent cohesion. Sorry, the second part of the question?
The second part was that what range would the creep coefficient be for the tailings?
It's actually quite difficult to come up with a figure. So creep is something we ascribe to something we don't fully understand. So creep is not related to dissipation of pore pressures. It's sometimes people call it secondary consolidation. It's ongoing deformation under constant load or constant stress. But the question of trying to put a relative figure on it, what dimension do you compare it with? So if you're trying to convert creep to a strain, do you take the entire dimension of for example, the height of the dam as your reference? Or do you take one raise of the dam as part of your reference? You know, it's difficult to come up with a way of sensibly referring to creep in terms of a strain, because you have to compare it to some relative measure. So in the end, we gave up trying to do that because there's no realistic way of doing it. And we just looked at gross movements and how much movement or how much creep occurred over time. And it wasn't large. It was only of the order of 30 millimetres a year, something of that order, fairly consistently for quite a period of time. So this idea that creep can accumulate over time and eventually you reach a point when you've got another trigger as well, in this case, the loss of suction, loss of apparent cohesion, enough of a trigger to get it to fail. So that was the sort of approach we used. Arthur?
Okay, so the next question comes from Parth from Indian Institute of Tech, Hyderabad. And he says that in slide 21, you have shown that the height of the tailings dam is almost 80 meters and the dikes were constructed by upstream method. And also that there was no provision for decantation in the tailings dam. How much does all of these contribute towards the failure?
Yes. So there was no attempt at any stage to drain the tailings. So the tailings are located in a valley with quite an extensive catchment above it in a wet tropical environment, or semi-subtropical environment. So you've got ongoing input of water. You've got some seepage still coming out, but effectively you're trying to block the seepage. So the phreatic surface was able to rise to a certain elevation and possibly reach roughly an equilibrium, which wasn't changing all that much. But then you'd have seasonal wetting up at the unsaturated zone above without a connection to the phreatic surface. So there's no doubt that they contributed. This was an oversteep, overwet dam, marginally stable. So there's no doubt that a lot of things that were, they had the conditions that were right for making it a marginally stable dam. Arthur?
Okay. The next question comes from Mazia from Karlsruhe Institute of Tech, and he says that he's interested in the temperature measurements. Don't you think that the temperature variation can change that brittle behavior shown in the figure, and might have an impact on the failure?
Yeah, there wasn't any measurement of temperature. I'm not sure what he is referring to there, and I'm not aware that any tailings do have regular measurement of temperature. But it does raise an interesting point too, whether it might be worth monitoring suction. And if you monitored suction using a thermally based suction sensor, you'd get temperature as well. So you could potentially calibrate suctions against temperature. An interesting point. It might be worth looking at. No one, to my knowledge, monitors suction in a tailings area above the pretic surface. But in view of the fact that this was one of the triggers of failure, that would be something worthwhile looking into.
Okay. The next question also comes from Karlsruhe, and this is from Professor Florian. He says that, would you recommend to consider the sub-hydrostatic hydraulic gradient in stability calculations?
To consider which hydraulic gradient?
The sub-hydrostatic hydraulic gradient. Sub-hydrostatic hydraulic gradient.
Well, yes, you'd have to in this case.
Okay.
So it would actually be a worse case if you assumed it's hydrostatic, but you need to accurately portray what your hydraulic gradient is.
Okay. So the next question comes from Luis Torres from Huis University in South Africa. Let me just go through the question. And he says that you described the Fundão under Brumadinho failures as liquefaction failures, but he feels that in these two cases, liquefaction was the result of failure rather than the cause of it. What are your thoughts on this?
Yeah, you always grapple with this a little bit, chicken and egg, which came first. And I think sometimes we confuse the issue by overuse of certain technologies or certain terminologies that have developed over time. You could use lots of other terms as well. Some people have bandied around the idea of hydraulic fracture. It's probably that deep horizontal drain has been described as a hydraulic fracture event. Possible piping and movement of material, because again, that deep horizontal drain caused the seepage to be turbid. So you've got an element of loss of material. So it is a bit chicken and egg, and I don't think we should get too bogged down with terminology. As I said, we were charged with coming up with the technical causes, and one of the things you struggle with most is to come up with the triggers. Clearly, we know it failed. In this case, we had very good video evidence of how it failed and how quickly it failed. That doesn't tell you the trigger. That just gives you the observation that it failed. So we spend a good deal of our time working on trying to come up with the most plausible triggers, and we investigated at length all the possible triggers. And the two we came down to was a critical combination of ongoing creep. Some might call that progressive failure, but we don't want to introduce any fresh terms. So ongoing creep in combination with that loss of cohesion due to suction, or apparent cohesion due to loss of suction. And we didn't come by that lightly, and it was by a very rigorous process of elimination that we got to that point. Pardon?
Okay. So the next question that we have, perhaps we can take only a couple more. The next question comes from Sriful from Bangladesh, and he asks, how is the chance of failure of an in-pit TSF as CADIA to change to in-pit?
Well, if the tailings are not above the pit elevation, then they can't flow outside the pit. So in that sense, it's a lot more stable to have in-pit tailings. Effectively, you've got a wall all the way around. As long as there's nothing sitting on the tailings that are in pit, then you've got no potential to fail really. But Post-closure, you know, depending on what you do with the land post-closure, you might have something sitting on top of a cap, which is sitting on top of in-pit tailings. Then it might be a different scenario. But while you're operating it, necessarily the tailings are going to be below the pit level, the pit crest level. So where can it flow to? The only other danger might be sometimes you'll have open pits in combination with underground working. So there might be a potential failure that way from the pit failing into the underground. Next one, Papa.
Okay, so this one comes from Robbie Jordan from KCV Brisbane, and he says, do you feel all these data sources and assessment methods are luring operators into a false sense of security? He likes your idea of incorporation of operator efficacy.
Incorporation of what was the?
Operator efficacy.
Yes. I'm not sure that it's lulling people into a false sense of security. It shouldn't do. I think what it does do is it gives a time of warning that you know, the state of the art is not quite there yet. We don't have a method, particularly for predicting liquefaction type failures, to give us sufficient warning to get people out of the way. And even in the case of foundation failure, I understand Cadia did have some warning. They saw some cracking. They were able to observe there was an issue. In Mount Polly, another foundation failure, that was the initial trigger. It happened over a long weekend, and I don't believe they had any warning of that failure either, even though it was a foundation failure. The fact that the tailings flowed out was an artefact of water and slimes overtopping a deformed dam, which eroded it and caused the tailings behind to some extent to flow out. Not the entire tailings, they didn't totally liquefy, but some of them came out through the breach. So no, I don't think we're there yet. And the biggest safeguard, the best safeguard really is to make sure you've got adequate stability. I think that's the critical case. You know, in the case where you've got marginal stability, you're treading a difficult road. Arthur?
So we can take maybe perhaps one or two more questions, maybe one after that. So this one comes from Mayu Tinkopa. Sorry if I butchered your name. So he says that, or she says that, thanks for your presentation. It seems that the unsaturated behavior was presented and it was not clearly understood from engineers. Can we define a critical state line for a specific suction? Can we estimate the loss of suction as a change in void ratio? Is there a model to do that?
No. In short, no, there's not really an approach that allows us to do that. It's very difficult to test unsaturated soils or tailings because in the testing, as you load them up, you'll compress the air. So you're changing the pore volume, hence you're changing the degree of saturation, so you're reducing the suction, which will then automatically reduce your apparent cohesion. And the apparent cohesion, a way of treating strength from suction, is just it's just a bit of, I wouldn't go as far as calling it a fudge, but it's a simplistic way of representing the strength gain from suction, just to take it as an increase in apparent cohesion, increase or loss in apparent cohesion. It's a simplistic way. It's like getting access to your stress strain plot, which is going off at right angles with suction on the axis. So the simple answer is no, we don't have a way of accounting for it. I think I'd turn around the other way and say, if you don't allow for suction, if you don't allow for any suction above the water table, then you're playing it safe, but you still have to have a suitably stable dam that you're working in. If you were to include suction, you could lose it through, for example, extreme weather events. Got time for one more, Butler, or is that about
There's just one. We have actually a lot of questions, but we'll take just one. I'm just trying to see which one is the best. Okay, let's go for this one. This looks to be a good one. So this one comes from Yashay Narayan Swami from Jones and Wagner, South Africa. He has a question regarding sample preparation method for remolded samples. Moist stamping seems to always produce contractive stress path, while slurry deposition methods always seem to produce initial contractive but then strong dilative response. Is there a preferred sample preparation method for tailings?
The ideal would be if we could sample them at their in situ state. And that's the great difficulty. We can get the critical state line readily because we do that on remolded samples, reconstituted samples. and then we move them. If we deliberately produce them loose or dense, and we load them or unload them in such a way as we head towards a critical state line. In some cases, we don't always make it. But you know, inevitably we can end up with a critical state line. So the critical state line's easy because we determine that based on reconstituted samples. What's difficult is to plot on that same graph where the in situ state is, and it's extremely problematic. So if you've got a tailings which is loose, contracted, likely to liquefy, you'll have a lot of trouble sampling it. If you've got a denser sample, you'll be more likely able to sample it. If you can sample it, it's probably dense enough that it won't liquefy. So that sort of defeats the purpose. I think there's a lot to be done there, and I guess we rely pretty much at the moment on some in situ testing technique like the cone to give us an estimate of where we are in relation to the critical state line. That's where we're at the moment. You can do a whole suite of testing, but how sure are you that you're representing the in situ state? Thanks, Partha. Good luck with your program.